In the today's class, we are going to start the law of mass action and equilibrium constant. See student, in the previous class, we have already studied the equilibrium introduction. Now in this class, law of mass action and equilibrium constant relationship we will study. Firstly, we need to understand what is the meaning of law of mass action. In the chemical reaction, you have so many reactants are present there. Once you will observe the reactant amount. So some reactants have so much enough energy so that they can easily react and to produce the product. But some of the molecules have not enough as much as energy, okay, that we needed to produce a product. So the reactants already they have some energy, so they would actively participate in a chemical reaction. So you can say the masses of that reactants who would actively participate in a chemical reaction, that relation of related to the law of mass action. Now how the equilibrium constant is related to this, let's understand. Whenever you will start a chemical reaction, like you have two reactants A and B, they are reacting with each other and they are producing the product P. So the speed at which the A and B are reacting and they are producing the product P, that is known as your rate of reaction. Like how much time these reactants will take to react and to produce the product. That is known as your what? The speed of reaction, you can say the rate of the reaction. How much time they are taking to reacting and to produce the product. So your speed of reaction or the rate of reaction, that will be directly proportional to what? That will be directly proportional, or you can say it will directly depend on the reacting species concentration which involved in a chemical reaction. In a chemical reaction, as we know, what is your chemical reaction? Initially you have only reactants and they are reacting with each other and they would produce a product. We know this thing. Clear? Now, so the speed of the reaction, that is what? Reacting species who are reacting and they are combining and forming a new product, that is the product P. So you can say the speed of reaction will depend on which thing? The reactant amount. How much you have a reactant concentration, that is directly proportional to that one. So you can say what is your law of mass action? Law of mass action are what? Firstly, we need to understand it will depend on the two things, or it is based upon the two things. First is speed of the reaction and second thing is what? The reacting species concentration. Simply, it will define a relationship, the speed of a chemical reaction and the reacting species concentration. The speed of a chemical reaction is directly proportional to the product of the reacting species who are involved in that reaction, their active masses who are actively participating in a chemical reaction. That is your law of mass action. So you can say whenever you have a chemical reaction, A plus B are reacting and they are producing the product P, and in a reversible manner this reaction is taking place. So it's a reversible reaction. So the speed of a reaction, you can say the rate of a reaction is directly proportional to the product of the concentration of the reacting species. Reacting species concentrations who are involving here, who are just involving here, the product of these concentration of the reacting species, the speed will be depend on this thing. Now here, once you will remove this proportional sign, you will get a proportionality constant. Proportionality constant is K. R equals to K A B. Now here we can easily understand this thing, that this is the relationship of the speed of a chemical reaction and the concentration of the reacting species. Now, application of law of mass action to the chemical equilibrium. How the law of mass action is useful in the chemical equilibrium. As we know, we have a chemical reaction in which we have two reactants A and B. They are reacting with each other and they are producing the product C and D. At this, after some time, what we are observing, that these are my reactants C and D for the reversible reaction. These are my reactants C and D. They are reacting with each other and they are producing the product A and B, you can say. So this is your complete reversible reaction. This is a reversible reaction in which what you are observing. Firstly, once we talk about the forward reaction, The forward reaction is what? A and B are reacting and they are producing the C and D. So this is my forward reaction. So the forward reaction is speed. Speed of the forward reaction is what? How much time A and B are taking to react and to produce the C and D. So the rate of forward reaction is directly proportional to the concentration of the reacting species. Speed of forward reaction is what is the meaning of the forward reaction is speed? Like how much time A and B are taking to produce the C and D products. So the speed of your reaction will depend on which thing? It will depend on the reacting species who are involved in a chemical reaction, on their concentration. So A and B concentration, it will depend on this thing. So rate of forward reaction, you are expressing, for the forward reaction you are expressing a subscript in a forward form, is directly proportional to the reacting species concentration, their product. Okay, so it will depend upon the product of the reacting species concentration. Now once you will remove this proportional sign, you will get a proportionality constant, that is Kf, the equilibrium constant for the forward reaction. Rate of a backward reaction is directly proportional to the concentration of the reacting species. For the backward reaction will takes place, C and D are reacting and producing A and B. So for the backward reaction, what will be your reactants? The C and D will be your reactants, can we say? So the rate of the backward reaction is directly proportional to the product of the concentrations of these species C and D which are involved in the chemical reaction. So once you will remove this proportional sign, you will get a proportionality constant, that is Kp. So Rb equals to KbCd. At the equilibrium, both the rates are equal. At equilibrium condition, what would happen? Both the rates are equal. You can say the rate of forward reaction would be equal to the rate of backward reaction. At the equilibrium, what we are observing, we have already studied, the speed of both the reactions are equal. Rate of forward equals to rate of backward. Rate of forward reaction, what you can write? KFAB equals to rate of backward reaction KBCD. Kf upon Kb equals to Cd upon AB. Kf upon Kb you can write, in place of this Kf upon Kb you can write Kc equals to Cd upon AB. So here we can understand the equilibrium constant in terms of concentration, that is the ratio of the product of the species involved in the reaction, and you can say it is the ratio of the products concentration upon reactants concentration. Okay, it is the ratio of these one. You will get a equilibrium constant. At a constant temperature, the product of concentration of the reaction products raised to the stoichiometric coefficient divided by the product of the concentration of reactants raised to their stoichiometric coefficient. Suppose you have a chemical reaction AA plus PV, it is producing CC plus DD. So here the A, B, C, D, these are my stoichiometric coefficients which are involved in a chemical reaction. Like you can say the amount. Suppose you have this 1 mole and you have this what 0.5 mole is there of these reactants and products. Now here equilibrium constant you will define product concentration upon reactant concentration. Product concentration is what? C power C. Here we need to involve these stoichiometric coefficients as well, because they would also affect the speed of a chemical reaction. As we can easily understand, at the constant temperature, the product of the concentration of the reaction product concentration, the product of these one, and raised to the power of their stoichiometric, because they would affect the speed of your chemical reaction. No? How much amount you have, suppose 0.5 mole. So your speed will depend on that amount, as we have studied. Your speed would be affected by this way. So here Kc would be equal to C power C, T power T, A power A, B power B. So this is the general way to represent this one. Now equilibrium constant in gaseous system. In gaseous system, once we will understand, in the gaseous system you have what? For the ideal gas equation, if we will see the ideal gas equation, just see over here this ideal gas equation, that is PV equals to nRT. So P equals to N upon VRT. N upon V would be what? CRT, moles per liter. Moles per liter, that would represent your concentration. Concentration would be expressed by CRT. So your pressure of your reactants, the pressure of the reactants, that is directly proportional to the what? Gas concentration, you can say. So the gas pressure, pressure of the gas is directly proportional to the gas concentration. You can express in this term also. Okay, now here suppose you have a chemical reaction AA plus BB. In a reversible manner they are forming CC plus DD. So suppose once we are talking about that, you have the chemical reaction which is taking place, the reacting species which are here, we are not taking concentration amount like molarity, normality. We are not taking any concentration amount to calculate their amount. Now we are not taking any concentration term. We are using the gaseous substance. For the gaseous substance, you need to include which thing? You need to include the pressure term. What you need to include? The pressure term you need to include for the gaseous substance. Clear? Because pressure is also a unit just to measure the things. So here Kp equals to, so you are expressing the amount in terms of their partial pressures. So whatever you have a reactants or products, you are expressing the amount in terms of partial pressure. So partial pressure of C power C, partial pressure of D power D, upon ratio for partial pressure of A power A, partial pressure of B power B. So you can express like as you have expressed the Kc in the concentration term. Here you have expressed the Kp in terms of partial pressure, because we have understood the partial pressure is directly proportional to the gas concentration. So concentration you are expressing in terms of partial pressure. Partial pressure for the reactants and products. Partial pressure of A. Partial pressure of A equals to what? Mole fraction of A into total pressure. Partial pressure of B is equal to the mole fraction into total pressure. Partial pressure of C equals to mole fraction into total pressure. Partial pressure of D would be equal to the mole fraction of D into total pressure. Now here Kp equals to partial pressure of C power C. So partial pressure of C you are expressing mole fraction of C into total pressure power C. Here partial pressure of D you are expressing in terms of this mole fraction into total pressure power D, upon here you have partial pressure of A you are expressing in this term mole fraction of A multiply by P and power A. Here partial pressure of B you are expressing mole fraction of B multiply by total pressure power B. Mole fraction of C power C, mole fraction of D power D, mole fraction of A power A, mole fraction of B power B. And total pressure you are expressing in this term P power C plus D minus of, here the pressure is what? The pressure is A plus B you can express. So once you are just go here, so this would become pressure power C plus D minus A plus B. So this would become mole fractions. Now here the mole fractions you can express in terms of Kc as well. We would understand this thing. How we are expressing? C student. Once you need to write the mole fraction for this C reactant. So what you will write? Moles of C upon total moles. Here mole fraction of D. This would become moles of D upon total moles. So here we have as we can easily understand. Now moles of C, moles of D. Here you have moles of A, moles of B. Like this way you are expressing. So Kc you are expressing in this term moles per liter. As we know, molar concentration we are involving now. So molar concentration is volume is 1 liter we are taking as well. We are assuming in this way. Okay. So here in terms of moles you can also express this thing. So here Kp equals to Kc and P power delta Ng. Delta Ng is representing the product moles minus reactant moles. It is the difference of these. Relationship between Kp and Kc, how you can express, like understand by this way. P equals to nRT, you know. P equals to N upon VRT. N upon V would express your concentration C. Now partial pressure of A would be equal to the CART. Partial pressure for C would be equal to the CCRT, partial pressure for B, CBRT, partial pressure for D, this would become CDRT. Now here, relationship between Kp and Kc. So you have expressed the different gaseous reactants. Suppose you have A plus B reaction, as we know that all they are in which form? They are in the gaseous form. So you are expressing their partial pressure in terms of concentrations as well. So relation between Kp and Kc. So you can easily express the Kp and Kc. Kp you have expresses partial pressure of C power C, partial pressure of D power D, partial pressure of A power A, partial pressure of B power B. Now here the partial pressure is expressing in terms of concentration. C power C, D power D, A power A, B power B. RT C plus D. RT upon में A plus B. Now RT C plus D minus A plus B. Now here Kp equals to what? This would become your Kc. So here these concentrations you can take in this way. You can express in this way Kc. Kp equals to Kc RT power delta Ng. So here in the place of this C power C, D power D upon A power A, B power B, here you can write Kc in place of this RT power delta Ng. Delta Ng is what? The product moles minus reactant moles. Product moles minus reactant moles, you can express Kp equal to Kc RT power delta Ng. Now here there are some questions. Let's discuss about that one. So we have understood the relationship of an equilibrium constant would be expressed in terms of pressure, equilibrium constant in terms of concentration, Kp equals to Kc RT power delta Ng. The following concentrations are obtained for the formation of ammonia from nitrogen and hydrogen at equilibrium at 500 Kelvin. Nitrogen concentration 1.5 into 10 raised to power minus 2 m. Hydrogen concentration 3 into 10 raised to power minus 2 m. And ammonia concentration 1.2 into 10 raised to power minus 2 m. Now the reaction is taking place. Nitrogen plus hydrogen, they are forming ammonia. A reversible reaction is there. Kc equals to ammonia concentration square upon N2 concentration, H2 concentration, Q. So here ammonia concentration 1.2 into 10 raised to power minus 2 square. N2 1.5 into 10 raised to power minus 2. H2 concentration 3 into 10 raised to power minus 2 whole cube. Now once you will just calculate this term, what you will find? 10 raised to power minus 4 in the above side. Here you have 10 raised to power minus 2. Here you have 10 raised to power minus 8. So this would become minus 10. Once it will go here, 10 raised to power minus 4, 10 raised to power plus 10. 10 raised to power plus 6 there will be. And here you have this answer 0.0355. How it will happen? 0.0355, 1.2 into 1.2. And here you have 1.5, 3, this 27. Now here this one, and here this one. What you are observing? 3 2s are 4, 9, and 3 3s are 4, 16 by this 45. And once you will just solve this value, you will get the answer 0.0355. Now here H2 plus I2, they are reacting and forming the HI. The concentration of H2, I2 and HI at equilibrium are 8, 3 and 28 moles per liter respectively. Determine the equilibrium constant. Let's understand. H2 plus I2 is forming HI, the reversible. Kc you will express in terms of product and reactant concentration, HI square upon H2 I2. As we know that Kc, how to write them? Product concentration upon reactant concentration you are taking. Okay, how many moles are there? There is stoichiometric coefficient, that is 1. So in the chemistry we need not to write the 1. So it is assuming that it is 1. Now here the HI concentration 28 and square upon 8, 3. So once you will solve this value 32.66. Now at a certain temperature, the equilibrium constant Kc is 16 for the reaction. This is my reaction. SO2 plus NO2, it is forming SO3 plus NO. This is a reversible reaction for which you have Kc value is given. If we take 1 mole of each of 4 gases in 1 liter container, what would be the equilibrium concentration of NO and NO2? Let's understand. Suppose you have initially taken the 1 mole, 1 mole, 1 mole, 1 mole. At the equilibrium, what would happen? As we know, some of the reactant amount would react and they would produce the product. So here you have 1 mole, 1 mole, 1 mole, 1 mole. At the equilibrium, what you are finding, from 1 mole, some amount will be dissociate. Some reactants are reacting and they are producing the products as well. So what you are finding, some X moles are dissociating. So some amount will be left over here. 1 minus X here. 1 minus X mole of this NO2. How much here will be formed? As you can understand, there is a molar relationship between these species. 1 mole of this, 1 mole of this, 1 mole of this, 1 mole of this. So here you have what? There is a relationship 1:1. So if X moles are dissociating, so how many moles here produce? The X moles of SO3 and NO will produce. 1 plus X, 1 plus X will be there. Now you can understand Kc value will be what? SO3 concentration, NO concentration, SO2, NO2. SO3 1 plus X, 1 plus X, 1 plus X whole square upon 1 minus X whole square. Now you can take the square root of this. 16 square root will be 4 equals to 1 plus X upon 1 minus X. Once you will solve, 4 minus 4X equals to 1 plus X. So this would become what? 4 minus 1, 3, 5X. X would become 0.6. So X value is 0.6. What is the concentration for the NO and NO2? NO is 1 minus X, 1 minus 0.6, 0.4. For NO2, 1 plus X, 1 plus 0.6, yani ke 1.6. Okay. So now by this way you can easily calculate. A mixture of SO3, SO2 and O2 gases is maintained in a 10 liter flask at a temperature at which the equilibrium constant of the reaction is 100. Now let's understand. You have a reaction, you have a flask in which you have the gases SO3, SO2 and O2. This flask capacity is 10 liter. Now Kc is given for the reaction is 100. Now if the number of moles of SO2 and SO3 in the flask are equal, how many moles of O2 are present? In the flask, suppose SO3 and SO2 moles are equal, then how many moles of O2 are present? That is the question. So let's understand about this one. Initially, we are assuming that N1 moles of SO2 are present and N1 moles of SO3 are present. Okay, because we have the same number of moles SO2 and SO3. So N1 moles of SO2 and SO3 are present. So the concentration of SO2 is N1 upon 10. SO3 concentration N1 upon 10. O2 concentration, O2 moles will be different, that will be N2, so N2 by 10. Now you are applying the law of mass action. The law of mass action you are applying. Kc equals to SO3 square upon SO2 square O2. Now SO3 N1 by 10 whole square. Here you have N1 by 10 whole square. Here you have N2 by 10. So this would be cancelled by each other. Here you have Kc value is 100 equals to 1 upon N2 by 10. So N2 value you have calculated. This is 0.1. N2 value is number of moles of oxygen gas is 0.1 moles of oxygen are present. Clear to you? Now let the second option is what? The second is if the number of moles of SO3 in the flask is twice the number of moles of SO2. How many moles of oxygen are present? Suppose we are assuming that number of whatever be the number of moles of SO3, the twice the number of moles of SO2 are there. Now he is asking number of moles of oxygen. So let's understand about it. Let the number of moles of SO2 is N1. For the SO3, how many moles are there? It is just twice of SO2. So this would become 2N1. Now for the Kc, you can calculate 2n1 by 10 whole square. And for the SO3, for the SO2, n1 by 10 whole square, n2 by 10. So here you have 4 n1 square upon 10 square. Now you have n1 square upon 10 square. All these terms will be cancelled. 4 upon n2 by 10. And here you have Kc value 100. Then what you can write? You can easily calculate the n2 value. This would become 40 by 100. So this would become 0.4 mole. So 0.4 mole of oxygen gas. Okay. N2 we have already considered the oxygen moles. Now the next question, the equilibrium of formation of phosgene is represented as, C student, phosgene is what? COCl2 is phosgene. When carbon monoxide gas, chlorine gas are reacting, they are forming the phosgene COCl2. This is a reversible equilibrium maintained condition. The reaction is carried out in a 500 ml flask. At equilibrium, what you are observing, 0.3 mole of phosgene are there, 0.1 mole of CO is there, and 0.1 mole of Cl2 are present. The equilibrium constant of the reaction is Kc equals to COCl2 concentration upon CO concentration Cl2. COCl2 concentration would be what? 0.3 mole. See, how many moles of phosgene are there? 0.3 mole. 0.3 upon mole. 500 ml. 500 ml means what? 10 raised to power minus 3 liter. 1, 2, 3. 0.5 liter. This would become 0.5 liter. So 0.3 upon 0.5. Here you have 0.1 mole of CO upon 0.5. 0.1 mole of Cl2 upon 0.5. Now you have calculated already what you are observing, 0.3 upon 0.5. And you have 0.1 upon 0.5. And you have 0.1 upon 0.5. So you have just simply cancel out all these things, and you have this terms are cancel outing with each other, and then you have 15. So Kc equals to 15. Now characteristics of equilibrium constant. I hope you all have understood up to that what we have studied. So in the next class, we would study about the characteristics related questions. We will do how the temperature would affect in these way, Q and K relationship, reaction coefficient and equilibrium. And in the further class, we will understand about the Le-Chatelier's and their questions related to that. So stay tuned with this lecture, students. I hope you all have understood, and if you will found any difficulty, and if you want that we need more questions, more topics related to that, so you can just subscribe my channel and you can just add some comments there. Thank you.